Welcome to the SAMPE Q&A for manufacturing technology. And thank you so much for taking time off your day and joining us. Let me start by saying that please be aware that this session is recorded and it will be eventually posted on the SAMPE's website for on-demand viewing. If you have any question, we want this to be as dynamic, as interactive as possible. So if you have any question throughout the duration of the session, please type them. There is a Q&A feature, and I do have it in front of me that is open that I can access. I just have to look to my other screen. And please make sure to interact with us. We want this to be as dynamic as possible. So let me go ahead and start by introducing myself. I'm your moderator for this session. My name is Ramy Harik. I'm an associate professor at the University of South Carolina, and I'm a resident researcher at the McNair Center for Aerospace Innovation and Research. I am a manufacturing aficionado. This is my passion, composites manufacturing, everything that has to deal with the world of automated fiber placement, be it from the design perspective, from the manufacturing perspective, from the inspection, as well as recently trying to embed as much as possible technologies from the world of industries of the future to the concept of automated fiber placement. So I'm going to start by introducing the panelists that we have today. And we do have an awesome lineup of panelists that we're going to speak with for their papers, as well as we have the winner of the best paper with us in this session. So yay for us. So we're going to be talking with Chen. He's from the University of British Columbia. He is a PhD candidate at the Composites Research Network at UBC, and he's working to develop faster cure cycle for advanced aerospace material systems. His research focuses on the fundamental effect of the curing condition on the microstructure and the resulting physical and mechanical properties. So we're going to go ahead and get started with Cheng after I finish introducing all of our panelists for the day. Next, we have Peter Caltagirone from the Colorado School of Mines. He is a PhD candidate at the Colorado School of Mines, and his research is focused around adhesive bonding of thermoplastic wind turbine blades. His thesis involves segmentation of the wind turbine blades to allow ease of transportation, larger blade manufacturing, and they live him and his wife in the beautiful town of Castle Rock, Colorado, and enjoy getting outdoors when the weather is good, or cooking or baking when the weather is bad. I cook all the time, Peter. So this is we have two common hobbies: composites and cooking. Unfortunately, the outdoors in South Carolina right now is a big no-no. It's very hot. Then the third speaker is Frank Palmieri from the NASA Langley Research Center. Frank is a good friend of mine. He is a senior research materials engineer at NASA Langley, and he's currently studying manufacturing challenges for processing and assembly of composite structures. He's been at Langley from 2010, and he has studied microfabrication and surface science for the manufacture of micro-optical and semiconductor devices. So Frank is our third speaker, and we move on to the fourth speaker, and I'm hoping that by now he has joined us. I don't see he has joined us yet, so we're going to skip Başar from Roketsan for the time being and move to the fifth speaker, Gail Han. Gail is one of the senior technical fellows at BRT, Boeing Research and Technology, and I'm gonna use the slide that Gail is using to introduce her. She's a technical fellow. She's a program manager for rapid high-performance molding of small parts, which is a DARPA and Boeing co-funded program. She also serves as a North American representative to the SAMPE Global Board of Directors. Gail, is there anything you would like to add before I do that? You have, you're part of the first place outstanding technical paper. We're so proud that you are in our session.
Thank you. Nothing to add.
All right, awesome, Gail. Moving on, we have Rose Roberts from BTG Labs. Dr. Roberts is a senior materials engineer at BTG Labs. BTG is a material science-based technology company specializing in surface treatment, process improvement, and surface inspection instrument technology. I love your devices. We use them very, very frequently. Dr. Roberts is responsible for optimizing surface preparation methodologies for improving adhesion reliability, determining the root cause for poor adhesion performance, and customizing surface preparation for a wide variety of industries and applications. She has a BE from Purdue. Boilermakers, I'm trying to remember what was, I spent 6 months at Purdue. Boilermakers, right?
Yep, that's right.
In chemical engineering, and a PhD in material science and engineering from VTech. So thank you so much, Dr. Roberts, for joining us. Least but not last, from Solvay, we have Fabio Bressan. Fabio works on process simulation methodologies at Solvay Composite Materials, and he is located in Anaheim, California. So thank you so much for all of you for joining us in this session today. And this is quite exciting that we're going to be talking together. The way that we're going to go about this is we're going to start talking with each one of you about some certain questions that we have about your work. And then we're going to move on to the generic discussions. And at any time, anyone in the attendees, if you have any question whatsoever, please feel free to type it in the Q&A. So Cheng, I'm going to go ahead and get started with you. So your work is on the effect of fast cure cycles on mode 1 and mode 2 interlaminar fracture toughness for interlayer toughened prepreg composites. So in your presentation, we've noticed on slide 10, you marked the microstructure of samples cured with all curing cycles as thinner interlayer, but the one cured with CC2. From the picture, to me, the one cured with CC2 is as thin as the one cured with CC1 or even thinner. Can you explain a little bit more about this?
Yes. So can you hear me?
Yep, we can hear you loud and clear. Go ahead.
Yeah. So for this material system, and if you want to, so is your question why the particle the interlayer get thinner, or sorry, could you shortly repeat your question?
Yes, I would be more than happy to. So what we're looking at is you're comparing your different samples of cured with all the curing cycles as like thinner interlayer. And you have marked the microstructures of your sample, but the one cured with CC2. So we're looking at the picture, and the one with CC2 is as thin as the one cured with CC1 or even thinner. Is that true? It's not true? Can you explain more about that?
So CC, actually, so first the CC1 is a standard Q cycle and with a heating rate of 1 degree C per minute. And the CC2 is a faster temperature. We have a faster temperature ramp and to a standard hold temperature, 180. So that's the difference between CC1 and CC2 they have different heating rates. So actually, and we did so here we just present two images. So it's very actually they are very typical representative images for those two Q cycles. But if we want to figure out and which is thinner and which is thicker, and we need to do lots of microstructure analysis. And what we found is the interlayer thickness for CC2 and is slightly thinner than CC1, and based on large quantitative image analysis. So the reason for that and why CC2 is slightly thinner is because CC2 has is about the gelation temperature. It's about the gelation temperature of the resin. Because so why the particle will deform? Because if we have a faster temperature ramp and resin doesn't get enough time to gel, but because the glass transition of the particle is at around 150 degrees C, and which is below our hold temperature. So if we have a faster temperature ramp as the CC2, and when the particle becomes rubbery, and when the temperature is above 150 degrees C, and the resin is still fluid, so the particle can be deformed. So it's all about but on the other hand, if the gelation temperature is below the glass transition particle, and the particle will not deform, even the particle is rubbery state, because the resin is already frozen. So the deformation, the degree of particle deformation is strongly linked to the gelation temperature of the resin. So as we can see, so the gelation temperature, we test the gelation temperature. The gelation temperature for CC1 is slightly lower than CC2. So the interlayer thickness for CC2 is slightly lower.
All right, cool. Yeah, thank you so much. That clarifies it. So have you ever tested mechanical properties of this material without thinning the interlayer, like maybe by curing it with a lower temperature but long time, just to see the effect of the deformation of toughener particles and thinned interlayer?
Yeah, and we did that, and we just published a paper in Composite Science and Technology, and to describe and the fundamental causes for about the particle deformation. And for example, we did there are two. So we did one Q cycle. It's a 0.1 degree C per minute temperature ramp. So it's very slow temperature ramp. So before the glass transition of the particle, and because the temperature ramp is so slow, so the advance of the degree Q is so high. So the resin gelled very early before the glass transition of the particle. So the particle, so when the temperature go above the TG of particle, and the particle cannot deform because the resin is already gelled. So you see spherical particle instead of ellipsoid particle. So the particle, because the particle is not deformed.
Thank you so much, Cheng. I have a question relevant to sharing the slides. I think from EL Tiosano, all the videos for all of these are already available, if I'm not mistaken. And you can actually access the slides as well as check the videos, EL. So thank you so much, Chen, and all the best. So you are in your 4th year PhD. So you're soon going to be moving to the final stages and defending your dissertation.
Yeah, I think it is so. It should be earlier, but you know the situation now. So maybe it will be delayed after September.
Why? What's happening now? Nothing is happening.
Yeah.
I just want 2020 to be over as well.
No, actually, so because I came back to China, so I don't know when I can come back to Canada. Maybe after September. So I prefer go back and to do the defense. Maybe I can do it online, the defense online. But I prefer to go back and to do the defense.
I understand. These are very challenging times with so many challenging situations, and best of luck for you. And
thank you very much.
Actually, I'm very grateful that SAMPE managed to keep the flavor of SAMPE, and here we are today discussing about all of this. So with that, future Dr. Chen, thank you so much, and best of luck on your and we're gonna see more questions if we have. I'm gonna switch to another PhD candidate, Peter Caltagirone from the Colorado School of Mines. Peter, how are you doing?
Good, thank you. Yeah, and honestly, I appreciate it because you got my last name perfect. Said it just right. So
I'm glad. I actually everybody massacres my name. Nobody says it right. So it's kind of my way to say the word. You know what? I'm gonna make an effort. But it's totally fine. So Peter, I'm glad to have you. So you're a PhD candidate. Which year are you at in your studies?
yeah, I'm right at the end as well. So my goal is to defend this coming December. So I'm almost done.
All right, best of luck. So I'm gonna start with a question. So your paper is determining mode 1 fracture toughness of adhesive composite joints, autonomous crack tracking using MATLAB developed program. So a little bit of a generic question. How do you see the influence of this project? In some sense, how does this can trickle down to industrial use?
Yeah, absolutely. And I'll go ahead and share my screen just to give a little bit. It'll help to illustrate my point better. So you should be able to see this slide here, correct?
Yep, we see the slide.
All right, great. So there is a standard out there right now developed by ASTM to determine the fracture toughness of a double cantilever beam. And I have an image you see on the right here. And there are hinges that are adhered on right off screen to the left here. And you would make markings that look similar to this on the side of the sample and then load the sample in a machine. And then either during the test or after the test, manually mark essentially as the crack passes those markings, then you note the displacement and the force at which it passed those markings. So, it's honestly not a very difficult test to do, but it is a very, very tedious test. And
so I'm gonna interrupt you because we had to do this at one point, and we had to create one bizarre system to actually get the data. So do you do everything on one machine? Like step number 6, analyze the recorded data.
Yep.
How do you, what do you do there? And then I'm gonna tell you what trick we did, which is a little bit ridiculous, but it worked.
Yeah, so this is going through the ASTM version of the steps, right? And so analyze the recorded data. How I did this after my test, because I didn't make markings on the samples that I tested, is I used ImageJ to measure the crack length manually, and it was about 40 to 45 minutes per side of the sample. So it took a long time to do. And so like I said, the tests themselves aren't that difficult to do, but the analysis is very, very tedious and can be very frustrating. And so what my program does that I wrote is, I'll just kind of skip ahead in this video, which you should be able to see. So basically it goes through and it measures the crack length for you automatically. And it does that because it can find the edges of the sample in the first image, and then it knows the number of pixels, and you provide it with the thickness of the sample, so it can correlate the two. And then you can see here, I'll back up just a little bit. So you can see here, I have a single black line that I draw on the beginning of my sample that just indicates that's where the crack start is, because it does have an initial crack. And then after that, so you see it starts at 50 millimeters is the initial crack length on this, and then as it continues, you can see that it follows that crack tip, and that's getting in the way because that pops up later, but it's sitting there obviously during this. So anyway, so you can see right that as it gets to the end, it follows it very, very well, and then it automatically exports all of the compliance plots for you, and then it writes the fracture toughness values, the 3 different methods of calculating the fracture toughness values indicated in the ASTM standard into an Excel file, along with the flexural modulus. And so how this is really helpful for industry is that using this program, it can eliminate a lot of the time required for the analysis, and save a lot of money, honestly, and also a lot of frustration and pulling out your hair just going through the tedious analysis. So Yeah, does that answer your question?
Oh, that definitely answers my question, and it makes me a little bit jealous that you have this, because the frustration you mentioned is actually, I mean, we did an amazing work and it ended up like being published in premium journals, but we had to do a lot of tedious analysis. I do have a follow-up question. I see that you have G1 and G1C. Does it make sense to look into G1P, or like, why did you pick these elements to take a look at?
Yeah, so this is just the fracture toughness, and then the compliance calibration method, and then the modified compliance calibration. And those are just the methods that are defined in the ASTM standard. So I wanted to, the reason why I chose these is because I wanted to stick as close to the standards as possible, just so it was usable, you know, for anyone using that standard. They would still be able to just develop the samples in the same way, but instead of creating, you know, a lot of markings on the side of the sample, creating just a single mark, and then, you know, putting it in the machine and having the code do all the analysis. So that's the reason why I chose those.
Yep, and thank you so much.
One other just very quick point that also is you know, really good to point out for the use in industry is that the left plot here shows the data points from my test that you just saw running, and then the right is the data points as if, you know, you're manually going through. So there are 18 data points, and so one of the issues is if there are any crack jumps that occur or anything like that during the test, then you know, normally with only 18 data points, that could completely skew the data. Whereas if you have, in the case on the left, I believe this is over 800 data points, you can see it doesn't skew the data at all, and there is a 6% difference in the calculated fracture toughness between the two plots. And the number of data points is completely just dependent on the rate at which you're collecting images and data for the test. So you could have 1 million data points. It would just, you know, take the program longer to obviously go through. But that's also an important note to point out.
Yeah, I mean, this goes into my next question that I had for you, which is what's one of the most interesting discoveries and most surprising with your research?
Yeah, and I think that is going back to the ASTM standard, right? The original standard, I think, was written in the 70s, if I'm remembering correctly, or maybe 80s. I don't know. It was a while ago, and obviously they've revised it over time. But you know, in the day and age of the computational power that we have today, it was surprising to me that there aren't, you know, programs out there available for free already for doing this analysis or anything like that. And surprising to me to see just how much of a difference something that you can adjust the rate and the number of data points can make on the end result. So,
Peter, thank you so much. This is awesome. Thank you so much for sharing this, and best of luck for your graduation defense in December. Hopefully everything goes as planned, and 2020 decides that, you know what, I'm gonna let things start going smoothly. And so thank you so much and best of luck.
Yeah, thank you.
All right, I'm going to go ahead to switch to Frank. Frank, you did have some interaction in the chat. I'm just seeing it right now with Peter. Do you want to go ahead before we start with your paper? Do you want to go ahead and ask your question?
Sure. Yeah, I'm kind of curious. It sounds like an interesting tool that Peter developed there. We do quite a bit of double cantilever beam testing in our labs because we're interested in bonded joints. And I've noticed there's a lot of so particularly with respect to bonded joints, because adhesives are so tough, linear elastic fracture mechanics are often not applicable, and so the result you get from using a modified beam theory method to determine the fracture toughness of an adhesive is usually characterized as inaccurate, simply because LEFM doesn't apply. So because of that, I've heard there's quite a bit of effort to use basically create a new ASTM standard using the J integral method. And I was just wondering if Peter's tool could be used, or if he knows about that method and potentially could modify his tool for that purpose.
Yeah, that's a really great question. I honestly am pretty unfamiliar with J integral. I did a little bit, or I remember learning about it a while ago, but I haven't done anything with my code with it. So does it require the crack length for the J integral?
And I think that's one of the benefits, is it does not use crack length. I think it essentially depends on the angle of the adherent at a certain point. So perhaps say where the load enters the adherent, what is the angle of the adherent tangential to that load point, something like that. I'm not developing the code. I'm not familiar with it really either. I'm more of a user. So, or the method.
Yeah. Well, so based on your description, it should be possible to modify the code to allow for a J integral, because, at the end of the day, really, it's just finding pixels. So adjusting exactly what pixel it's looking for and how it finds that is what would have to be changed, which is not something extremely difficult to do. So, yeah.
That's awesome.
But thank you. I'll look into that. That sounds really interesting. So.
That's good. That's very good. Thank you so much for this discussion, Frank and Peter. So, Frank, I'm going to switch to you and we're going to start talking together. So first of all, I want to verify that I understood your paper the right way. Your work, you're looking into getting rid of adhesives and trying to come up with new resin system, where the resin system actually is what, when you're doing secondary bonding or follow-on processes, it's the system that will actually diffuse and will actually act as the adhesive in order to generate adhesive-free bonding. Did I understand your paper right?
Yeah, so the idea is the material and the process we're developing is that hopefully would allow a manufacturer to use a secondary bonding process. So essentially a two-step assembly process like we're normally using when we bond something together. We make the part, and then you assemble it with an adhesive, and you cure that adhesive, and you have a bonded structure, right? And we want to be able to use that same simplified manufacturing process to allow us to build very complex, large complex structures out of a multiple of smaller, simpler parts, because that's a great way to build these large complex structures. But we don't want to have the reliability issue concerns we have with bonded structures, which require us to put in redundant fasteners. And so the technique that we're developing at NASA is a material that you put on the surface of the part during the fabrication, during the cure process. And I'll kind of jump to, hopefully I'm sharing my screen, and I'll have to put it in presentation mode.
Slides, yes.
Okay, and I'll skip to the, I guess I wish so I'll skip to this slide. Oh, of course there's audio.
No worries, and we're actually seeing your screen with your notes, which is totally fine. I mean, no problem with that. You don't need to switch.
Oh, okay. Okay, that's fine. So all I want to be able to show is the animation of how the process works. And so what happens is we're applying a material to the surface of the preform that's been offset in the stoichiometry. So this is an epoxy system, so it's epoxy rich in this case, and there's very little hardener in it. But when it goes to the cure cycle, the surface remains only partially cured. So that's what I'm showing here. This is a little frustrating though, because I have this. I'm using the version of the talk that has my automated stuff in it, so it makes a video. But anyway, now that I'm showing everything,
absolutely no worries. So
yeah, so it goes through this cure process, and the key is that in the Arabon process, the surface remains partially uncured, such that you can then assemble those uncured surfaces into a joint with a hardener-rich layer that can then provide hardener to that epoxy-rich layer that's deficient in hardener, such that in the secondary cure process, what would be the bonding process, you can have then a homogeneous material with the proper mixture of hardener, proper ratio of hardener to epoxy, just that it fully cures and you have a co-cured joint. And so it's a little complex to describe in words, but hopefully the picture is showing what I'm trying to describe, such that you can have a co-cured joint, but in a two-step process, so that you can use a bonding process scenario. And this slide kind of compares it directly to what you would expect for a bonding process, where you make the parts, you then apply a surface treatment, something with like a sanding process maybe, or something more sophisticated, hopefully. And then you assemble those parts with an adhesive layer, go through a second cure process to cure the adhesive. But then in the case of the adhesive, because it's not co-cured, there's a high chance that you're going to have to add additional fasteners to that to meet certification requirements. And so that's really where the AeroBond process benefits, is you can eliminate those redundant fasteners potentially because the structure is co-cured. So hopefully that kind of presents the technology in a nutshell.
Can I ask a question, actually?
Oh, can you hear me? Can you hear me? Sorry, Frank.
You're
can you
muted.
I hear two people now. I hear Ramy, and if you want to ask a question directly, that's fine with me. It's up to Ramy, I guess.
All right, cool. So I'm going to go ahead and get started. I think you can hear me now. Sorry, I was... so the first question I have is, I'm looking at the process of AeroBond on the left, and is there a certain time where you have to go ahead and proceed with the assembly when you use this material in the primary cure or not? Because, I mean, the state-of-the-art process that you describe as the one that we're all familiar with, you cure something, you don't really care how much time passes, then when you're gonna get back and do it, and you can transport it from one facility to the other, you transport it and you do the surface treatment and the adhesive assembly and you proceed. My question is, are there limitations when it comes to your process, when it comes to you have to start the assembly within X amount of time?
So that's a pretty good question. We haven't studied how long the surface is stable, but once the part comes out of the autoclave from the primary cure, we've had experiences between 1 day and a week, and we haven't seen that as a variable that's of significant importance. On top of that, I will say that the surface material, that partially cured surface, although it doesn't have a TG anywhere near the TG of the bulk laminate, the TG of the bulk laminate might be close to 200C, right? If it's a 350 cure, a 350F cure material, or 177 cure epoxy, the surface probably has a glass transition around 30 degrees C, something around that, and so it's glassy at room temperature, right? Unless you have a really hot working environment, it's a glassy material. Because it's glassy, there's not really any progression of the material of the polymer to advance to a higher molecular weight in gel.
Okay, that's awesome. The second question I have is, like, in my head, I know how when we talk adhesives, you're looking into, you want it to have cohesive failure, right? You don't want the interface failure. You don't want other, like, all these 6-7 other types of failures. How do you characterize failure? I mean, you guys definitely are doing a destructive test afterwards and so on. So how do you assess this?
Right. So for our process, there is no distinct interface. So in a bonded joint, right, you'd expect you have a fully cured adherent, then an adhesive layer, and the line between those two is a distinct change in materials, right? And that is susceptible to adhesive failure. But in the AeroBond process, because for the process to work at all, we need to have reflow of the resin during the secondary cure process, and we need to have an intermixing of those layers, just like you would when you have 2 layers of pre-preg that are cured during the primary cure, right? So if the AeroBond process is successful and we have a process that works and gives us an intermix layer, the only failure mode that's possible is cohesive. So if anytime through the development of the process, we occasionally had some processes that didn't work, materials that didn't have the right formulation, or a cure process that didn't provide sufficient mixing or something, and we would have an unmixed interface, and we would see we would see essentially it would look like an adhesive failure, right? And that's because maybe one of the layers flowed, but the other layer was too cured and did not flow. So we ended up with an adhesive bond that was just weak. And so those were just, in the process of developing air bond, on the way there, we had bad choices in our process. But now that we've had luck with a few different configurations for the system, for the material selection, and for the process. And so those parts generate joints that only fail cohesively.
Frank, I have so many more questions, but I'm gonna refrain for the time being because this is very interesting. I'm just gonna ask one more question. What's next? Where are you in the work right now, and what's next for your project?
So let me skip to where we kind of ended right before. So this project was a part of a 2-year effort at NASA, and I'll just skip to kind of one of our best data sets so far. And during that 2 years, we needed to show feasibility of the technology. So it's kind of in its infancy, and so we wanted to make coupon tests and show that we can meet or beat co-cure properties. And over about a year and a quarter, we did some process development, materials development, and started doing coupon level tests. And what we showed with these end-notch flexure tests, if you're not familiar with end-notch flexure, it's a test to measure the shear toughness, so the mode 2 fracture toughness of the joint. And we showed that we were not able to just meet, but we actually exceeded the fracture toughness of an analogous co-cured joint. Based on 8552 matrix resin. And so we showed on these 3 different samples. Each sample had 6 specimens that we were able to meet or beat the co-cured properties. And so we showed this with end-notch flexure. We want to expand this to a variety of coupon scale tests. So DCB, also strength tests like lap shear and flatwise tension, things of that nature. And we also want to do some fracture toughness tests, some impact and compression tests, or some durability, damage tolerance testing. And then beyond that, we want to scale up from coupon to sub-element, and we have a plan to do a test on a skin stiffener.
That's nice. Frank, I'm gonna stop here, and thank you so much for the nice discussion. I'm looking forward to more discussions later on, and thank you so much, Frank. I'm gonna move to Gail. Hello, Gail. How are you doing?
Just fine, thank you.
All right, awesome. So let's go ahead first of all and say that big congratulations. You are we are going to talk about the first place outstanding technical paper. You guys, your work is the winner on this, and it's very, very interesting. We're going to talk about compression molding of complex thermoset laminates. I've been hearing for the last few years is that the aerospace industry has to catch up with automotive, and we have to do this, and we have to enhance the throughput and high rate and so on. I guess you guys did it. So tell us a little bit more about the project.
Well, I want to thank you for the award, and I want to thank you for the opportunity to talk today. I'm filling in for Travis Adams, who is celebrating a new daughter. So that's a wonderful thing as well. Under the Tailorable Feedstock and Forming Program of DARPA, a 4-year effort, there was a tailorable universal feedstock for forming developed by University of Delaware. On the Boeing side, we were doing the forming side, so resin infusion, thermoset, and thermoplastic forming. This paper highlights thermoset forming, and it highlights one particular undulating structure. And in case it sounds like everybody doesn't have slides, this structure is a 1/4-inch structure made primarily with unidirectional material. And I wasn't really pleased with the way these photomicrographs looked for the end results. So I wanted to show that, we had very nice uniformity of the plies in this undulating structure. We do have some porosity, but not horrible porosity. We do have unidirectional plies with a fabric ply on the outside. So you're seeing the fabric plies here. But I wanted to give an idea of the quality that we're seeing out of this part. Limited porosity. Again, we do have a little bit of a crack perhaps here at the interface to the cloth. And we did find this one area, which is in section A, outside of the main part, with some cracking, but overall very, very good quality. So wanted to just share that this saved us a great deal of time. In the paper we discussed that we did a hand layup version as well. And with that, I mean, we're talking 3 shifts. When we're doing compression molding, it is much faster and also, we believe, more reliable for quality.
This is awesome. So I have a couple of questions for you. The first one is, so the shape that you guys picked for the trial, where does this come from? Like what's behind the complexity of the shape?
Well, you know, it's interesting you say that. We have a whole series of shapes that we did looking for features, because this was all about the development of the process and what the features are. So undulating structure, yeah, a wavy part. We did a curved channel with 2 different radii for the curvatures. We were going to do a Z channel as well. We did not do it at the time because we had so many other features we were doing. And when we did this undulating structure, we actually had some people with Z structure come by, see these parts, and as a result, we did some trade studies on Z structures as well. So, you know, radii are difficulties. Certainly the male, female shapes, you know, how you're doing your tooling, this kind of brings all of that together. And so, I mean, it was a challenge.
I agree. I like the shape. Like when I saw the shape, it does look ruled for me. It does look that the whole shape is ruled. Like, so you have one line and you're moving along a complex shape. It's not doubly curved. Have you tried doubly curved shapes, or is this
We have
something
done some curved shapes, and again, some of it is not all in thermoforming, but yes. And if you've got other ideas of challenges of shapes, we're always willing to hear that. I know when we presented earlier in SAMPE at 2 of the other sessions, we've asked all of the audience, throw your problems at us, because we will only develop a stronger process if we know what your problems are. And it was interesting to see that Fabio is going to be speaking later on. One of our parts was a beam. And one of the complexities, I mean, you're always looking at porosity, right? You want to eliminate porosity. You're always having the issues of wrinkling. But in one of the parts that Fabio has, we went from a 1/10 inch thickness to a 1/2 inch thickness. And the other thing that we got into problems there is resin flow. You can imagine that thick section wanted to go to the thin section. And, you know, what do you have to do in debulking? What do you have to do in the tricks of the trade for being able to do that? Or do you just say, hey, this is an R&D project, but for production, we would recommend that you don't go quite this extreme, or, you know, have more of a taper or whatever. And so a lot of the work we were doing was looking at different configurations so that we could start to put the boundaries on guidelines for design, for structural analysis, and for non-destructive testing even. You know, in some of these, if you were really doing these in production, you would standardize on some of these radii so that you could have shoes, you know, transducers so that you could read them. Otherwise, you're doing a lot of A scanning. Another thing that was really important was what is the driver? Is the driver lay down, or does the driver become inspection? What kind of inspection do you need? So depending part to part, it was all over the map, but very challenging.
That's all. I can only imagine. So you did touch a little bit on that, and which is relevant to going to production. So how many more trials you envision before you actually transition this from the R&D slash current environment into actual production?
That has been hotly debated throughout our program. In some of the configurations, we actually did pathfinder parts, just made sections, maybe and sometimes wooden tooling, looking at forming, other times small tools just to look at certain features so that we could decide how to do the tool design as well. So that's a really good question. Jan van den Brand, who is the program manager at DARPA, is a big modeler. He would love it if I could say we can make the first part and it's good. I don't think that is achievable in a new family of configurations.
Okay.
Now, we have made some ribs where after several ribs, we've got the process down, and then if it's just a matter of scaling for size or something like that, you might be able to make the first one. You're probably going to do a destruct on that anyway. So I would say 3 parts maybe. 8, something like that. On the one that I mentioned that was 1/10 inch to a 1/2 inch, I mean, we made...
you did show 8 parts, right?
We did 8 parts on this particular part before we replicated the last 4. So we have done 8. In a replication in the same family, maybe 2 or 3. If it's a totally new geometry, it could be more than that, if it's something that we don't have any idea for. And what you really want to do is couple that with the modeling. But to say modeling alone is going to do it all, sometimes we just don't know how to put into code what happens in all the physics, right?
I completely agree with you. I mean, in my area, automated fiber placement, I'm becoming a little bit more and more a fervent believer that physics will never get you to model all the defects that you can expect to have, and that some other techniques, data-driven techniques, usage of new techniques are needed. I do have one more question for you. I'm sorry if I have a lot of them. So what is the maximum part thickness or ply count that you guys tested? Like, what's the maximum part thickness that you've reached?
So the maximum that we did under this program was a 1/2 inch. And we
inch.
did have to pay attention to exotherm in thermosets. So again, you know, we've done multiple tracks. The answers are different in multiple tracks, but you still need to be intelligent and do your homework. That said, the tool sets that we have in modeling, the basic analysis, you know, heat of reaction, knowing what you might get into, you know, at the initial program, we were criticized because we were mimicking automotive, but rather than going for the 30-second or the 3-minute cure, we chose a 30-minute cure, less than 30 minutes time on tool. We've been successful in that area, and one reason is we wanted safety and we wanted quality parts. The other thing that we found is when we go from automotive chemistries and try to get to aerospace, it is almost impossible.
It's a different
if you
beat.
go from aerospace chemistries and try tricks to speed them up or offline, post-cure, whatever, you can actually achieve quite a bit.
I agree with you 100% on this. So I actually lied and I said that was my last question. I do have one more quick one. So why thermoset? Why not thermoplastics?
We also have a thermoplastic track. Thermoplastics are very good. In some cases, people are concerned about not having thermoplastics. So a lot of our work is DOD. If it doesn't have thermoplastic application, they want to be able to use their thermoset repair. They might want to use their thermoset coating processes and the like. So thermoplastics absolutely has its trade space. We also did resin infusion. It has its trade space. The nice thing about thermosets and about this particular thermoset, 5320-1, an out-of-autoclave material already. We're using it in a different kind of out-of-autoclave, right? In a press. It has a large database. If we can tie into that database and all of the other things about trim and drill and coatings and everything else, it's a wonderful thing. It makes it much easier to get those first transitions. So absolutely, in a trade space, you want to have a lot of things in that menu because it differs. It differs depending on the trade, but absolutely an important part of it. And thermoplastics will have their home, and they are also certainly moving forward.
Okay, I'm glad to hear that. And I can't wait till we see what you guys are doing on this. So Gail, thank you so much. Once again, big congratulations, and please congratulate Travis. So in Lebanon, we say when you have a baby girl, good news comes with your baby girl. I guess Travis had the baby girl, and he won the first place outstanding award. So please transmit that to him.
I certainly will. Thank you.
My pleasure. So I'm gonna switch to Dr. Roberts from BTG Labs, and we're gonna be talking with Rose on bonding to bulk metallic glass using aerospace grade structural adhesives. How are you doing, Rose?
Doing well, thank you.
All right, awesome. Let's go ahead and get started with, first of all, it's really interesting, the challenges, the bonded surface challenges. Can you elaborate on similar applications where your work has had benefits, like where you've seen that, hey, this is a big check mark for similar type of work for other applications?
So I don't have any specific examples from my experiences where I've seen something like this exact type of application before. But really any application where you're bonding a thin foil-like material onto a stiff substrate, we'll find some relevance in the work that we're doing right now, especially if that foil is fairly stiff and relatively difficult to plastically deform, such as a spring steel, and you're using a stiff adhesive for that bonding application. In this case, most applications can probably improve their adhesion to that thin foil by changing which adhesive you're using. Because our current running theory right now is if you have a more viscoelastic type of adhesive, that the bonding will most likely improve. We're still working on confirming that theory, but that's the running theory right now. But if you can't change the adhesive, like the Jet Propulsion Lab has a very strict tolerances on this optical edge that they're using. It's on the order of about 20 microns, and it has to maintain that tolerance through a really wide range of temperatures. So think, you're sitting in storage in a rocket in the Florida heat, and then, you take off into space and you're in the cold of space several minutes later. It's a wild temperature swing, and you have to maintain that 20 micron tolerance throughout that. So they use a stiff adhesive so that you have low creep. And so they have to use, very specific types of adhesives. And so, for most applications, you probably don't need that. So you can probably use a different type of adhesive. But the physics that we're learning about and understanding more deeply with this research can be applied to other areas.
All right. So if I understand correctly, the kind of application you're working towards is so specific. I mean, in the context of from Earth to space and so on, that this kind of application is very, very specific.
It's quite specific. There has been some literature research that we're continuing to find, looking at the thicknesses of substrates being bonded with stiff adhesives. And so there has been some research in the past, but it's a little difficult to know some other specific applications that are similar anyways. All
right, awesome. So can we classify this this problem as a hybrid bonding technology? If so, why? And if not, like why not? Where would you classify this?
So the bonding technology here is just, from what we understand, is just kind of, you know, it's a peel test is what we're using. So for my understanding of hybrid bonding technology, hybrid bonding technology is generally used for electronics chip manufacturing, which generally combines direct bonding methods with adhesives. Those material systems generally consist of silicon wafers and metal interconnects, and then sometimes adding some adhesive in there as well. You know, that technology relies on the surfaces of the two substrates bonding together kind of directly to form a material with little to no bond line, because the materials are basically becoming one. At least that's how direct bonding, we think how it works. But the application here, you're bonding a stiff adhesive to amorphous metal, and so it's not as similar to hybrid bonding.
All right, thank you so much, Dr. Roberts. Please send a hi to Gilles on my behalf, and looking forward for further interaction. I'm going to go ahead and switch for our last panelist, Fabio from Solvay Composites Material. Hey, Fabio, how are you doing?
Good, good, very good.
We're wrapping up strong with you. We have a couple of questions on your work, and go ahead and get started. I mean, whenever we have simulations, we always talk about mesh shapes and different meshes and their influence. So how will different mesh shapes affect the simulation results in your case?
So there are, you know, more obvious answers and less obvious answers. I'd like to share briefly the slides. So
please go ahead.
There we go. So I just noticed that in the attendances we have even Tim Lucchini. So I just say hello. So we are not alone in this project. So a lot of work all together. But so I add a couple of other slides talking about the you know, the mesh mapping and what we discovered during all this kind of work. So maybe back to the original slide where I mentioned there are two major aspects. So the fine and, you know, mesh, and defining the small dimension of the element and the orientation of the mesh. So talking about how small has to be the mesh, it's strictly connected to, for example, the curvature you want to capture and the definition and the details. That's pretty obvious. What is not really obvious is the fact that we decide to orient the mesh based on the fiber direction. So if we consider a fabric material, so what we decide to do, and that is a great example, you have your stacking sequence. Let's say the first layer is 0, 90 degrees, the second plus or minus 45, third plus or minus 45. That was a great intuition, because what we discover at the end, you have a flat panel with all the stacking sequence in the pre-preg condition, where this is the product, this is the material we see, and that mesh oriented in a very specific way allow the material card to obtain a better prediction in thermal performance. So that's the idea, and I cannot tell you too many details because it's something kind of secret, but this is a nice recipe.
So I have a follow-up question, and I think it's going to be in your next slide. Like, I think it's here. How do you simulate the wrinkles between the layers?
So So the wrinkle is it's something that maybe we can jump into more complex. I don't want to impress anyone, but this is a material card in LS-Edina and describe one of the most important aspects from the modeling perspective. So what we call the locking angle. When we have this specific condition, the material start to buckle outside of the plane, right? And this is extremely important because that is starting the wrinkling effect in plane, but even out of plane. So defining the interlaminar wrinkle, that is the most difficult part. We can see here, for example, where we attach the spring on the edge of the structure, and when we stretch the material based on the stacking sequence, let's say, for example, in the blue, we have a plus or minus 45, in the red is 0.90. Each layer act in different ways, so start to buckle differently, right? So how we can predict that and how we can simulate that? So we introduce that in specifically in HyperMesh, some TCL scripts where basically we identify mutual interaction between each layer. There is the contact definition, and the material card from the behavior of the material, but is connected to the behavior on interlaminar behavior. So that's the friction between layers and even with layers and the mold. So all this is a combination between modeling and material cards, so the capability to capture the material behavior. All this combining together allow us to actually capturing more complex wrinklings. Did I answer your question?
Oh, you definitely did, and this is awesome. I'm very, very thankful for the details you did, and I have to say the graphics are impressive. I do have a question. Is this project related to Gail's project that she presented? Like, is this?
This is part of the DARPA project, of course.
Okay, so this is part of the same DARPA project.
Yes, that's right. And there was an exciting long process. It's not just a few days of good ideas. Unfortunately, we had 90% of the failures and 10% of success. But now we show the 10% of success, of course.
Hey, that's not bad. Hey, this is I've had projects where I did not even smell success in them, but you always learn.
Yeah, no, we implement all this technology also in the automotive world, where sometimes the complexity of the shapes are extreme, and this technology is applicable in different area of the simulation, of course. And we are proud of these results. I think we had many challenges, and it was a great opportunity for us to investigate in details.
This is awesome. I'm very thankful for the discussion, and especially the connection, and looking forward to hear more about this. So I think this is we went a little bit beyond the hour, a couple of minutes more. So I want to go ahead and thank you all for participating in this session.
Ramy, I'm sorry to interrupt. This is Rocio. I just noticed that Başar had joined, but he joined as an attendee. So I'm not sure if we have a few more minutes, we can ask him just at least one of his questions.
Absolutely.
Thank you.
Definitely. Başar, can you hear us? Can you open your camera, your microphone? So.
Hello, can you hear me?
Yes, we can hear you. We're glad you could join.
I have listened all of your speech. I think you've seen me lately. Sorry for that.
All right. So Başar, I did not present you. You are working as a structural analysis and test engineer in Roketsan, Inc.
Yeah.
If my research is correct, this is in Turkey. Is that correct?
Yes.
All right, awesome. And basically what you've worked on is the investigation of the effect of thickness and surface roughness on adhesive joint strengths. And I'm gonna go ahead and shoot the couple of questions that I have for you, if you don't mind.
Yes, of course.
So what's the difference? What is the difference between the tested tensile strengths and the tensile strengths of the epoxy adhesive, if you have the data?
Basically, strength value can be found in data sheet, but these values are obtained from perfectly prepared specimens. For example, these specimens are prepared in vacuum chamber with optimum materials and surface treatments. Also, curing process are held in temperature controlled chambers. Another thing is generally shear strength of adhesives are given in data sheet. So in real applications, we couldn't done in vacuum chamber. These adhesives are applied with injectors,
Yep.
So air bubbles can be trapped in this type of joints. Also, bond line can be combined loading, for example, shear and tensile loading. So we have to test, we also have to test tensile strengths. It's a similar, it's a simple work, but in this work we have to obtain how is the difference in strength from data sheet and tensile test. For example, for data sheet value, it's 40 megapascal, and we obtained from not well prepared specimen 35 megapascal. That's the difference. It's based on manufactured strength, I can say.
Yeah, can you comment? I mean, I just have one follow-up question on this. The same question, but more in line relevant to the tested shear strength. So you got like the test you had was a tensile and the shear. So yeah. Was there like more correlation between the tested tensile and the tensile strengths, or the shear strengths, or the tested one and the shear strengths of the adhesive? Which one, like, can you comment a little bit more on that?
Yeah, I can comment. Shear strengths are more lower than tensile strengths because in bond line applications we always want to load a bond line with shear because it's more uniform loading. But in tensile strength tests, we obtained much more higher. It's an unexpected value, I think, but I don't know how can be done.
All right, this is awesome. I'm very, very glad that you managed to join us, Başar, and that we got to have this discussion. And thank you so much.
Thank you.
All right, so I think, Rocio, now is the time to close. Is that correct?
That is correct. Thank you, Ramy.
All right, cool. So I want to thank everyone for participating in this session. If you have additional questions, please feel free to fill out the form like that is on the track landing page on the SAMPE North America website, and SAMPE will make sure to follow up. Make sure to check the content being released next week for the following tracks: the aerospace application, market application, workforce development, and digital modeling. And it's all part of these awesome virtual series that Rocio, Brianna, and all the team at SAMPE are working hard to deliver to us. I also wore our USC SAMPE 2018 dedicated shirt. With that, once again, I want to thank Cheng, Peter, Frank, Başar, Travis, actually Gail, Rose, and Fabio for the presentation and the meeting today. And Thank you very much and all the best. Bye-bye, everyone.